Okay, so I think we went over CFS the last time, and it was, I think, a little unstructured, but still we went over most of it. Just as a very quick recap before we go to EEVDF, we discussed how CFS uses vRuntime to really track fairness and make sure that all the processes get their fair share of CPU. We went over a few terms called vSlice, shed period, and min granularity as well. We discussed how these things kind of interact with each other. We discussed how shed period is just one heuristic where we want each task to run at least once within this period.
Does it make sense to change the chalk because the route
You
is
can't see this.
really visible?
Is this visible at all? Or?
It's okay, but maybe for the next.
The next things you can.
Oh, no better.
Yes.
So the shed period.
Maybe white.
Writes the. You don't.
Orange might be perfect.
There might be some over there.
This,
Yeah,
this,
good.
yeah, see, better. So yeah, shared period is one heuristic where you want each process to run at least once. And this again is to do with the min granularity. And I think there were a few questions about exactly how these things are computed. So what we do is we check the number of running tasks. If it's n, we multiply that by 0.75. And let's say there's like 20 tasks, right? That gives us 15 ms. Now, it doesn't stop here. This is just the base shed period. Now, once that we have that value as x here, we compute vSlice. Now, vSlice is where the weights and the nice values come into picture. So if you have the base slice or base period of 15 ms, we weight that according to the nice values. So if you have 20 tasks, let's take one of those tasks, task A, and it has a weight of, let's say, 3000. And the base weight is 1024. So what we do is we take 15 and we do 1024. Oh, sorry. The base weight is 1024, yes, and 3000 is the task weight of one particular task. But let's say the total weight of all 20 tasks is somewhere like 30,000. Then we take 15 ms, we say it's 3000, which is the weight of the particular task, divided by weight of all tasks put together, 30,000. So that'll be 1 by 10. So this gets 1.5 ms. And let's say there's another task, task B, that has 300 as the weight, right? So that guy will be 15 into 300 divided by 30,000. So it gets 100th of this, which is 0.15 ms. But as we discussed last time, min granularity means that no task can get less than 0.75 ms. So this is adjusted to 0.75 ms. Right, and this continues for each of these 20 tasks. And what we have the end of that is a vSlice for each task. Now you can see that. Yeah.
No, I maybe like just recap for everyone. So if each task had the same weight, then each task would get 0.75 because the logic was number of tasks multiplied by 0.75. You get 15 milliseconds, and if you with the goal that each one gets 0.75. But now we say there are weights, and so we kind of like adjusting for the weights, but we never go beyond 75.
Yeah,
right?
this is the minimum. It is only adjusted if we get lesser. And that is why this is the base shed period. At the end, the actual shed period is all of these numbers combined.
So it can grow a little bit.
Yeah.
Because
again, this is another heuristic, right? So I actually had this one part saved for heuristics. So we can, as a fun activity, just like count the number of heuristics that we come across, and this keeps growing. It never stops. So I think shed period is one heuristic. Min granularity is one heuristic. And at the end of all of this, we have the slices. So once we have the slice,
What is the V slice? Can you remind us?
V slice is exactly the amount of time that a period, that a task will run for, unless it is preempted.
So it's what we just computed with
Yeah.
weights.
Yeah,
Like-
weight adjusted slice.
Mhm.
So we had 15 ms as the shed period.
Mhm.
And then we had the weight adjusted slice of 1.5 ms
Mhm.
for task A. That's the V slice for task A.
And
Right.
75 task B.
Yeah. So if
So that's
task
their
A,
V slices.
exactly. So if task A is scheduled, it will run for 1.5 ms until it's preempted.
Mhm.
Now, once we have the V slice, then we can actually start talking about exactly how CFS goes about scheduling things. So we have the scheduling period, and this is each tick. We discussed how ticks are at 1 ms granularity, but we have the scheduling period of, let's say, 15 ms. This is what we'll kind of look at to understand if CFS is working as expected. In 15 ms, once you've computed the weight adjusted V slices, that's how long we want each task to run. If A has a bigger weight, let's say 3000, for every 3000 ms of A, B has to run 300 ms. So if these are the weights of the task itself, we want to make sure that every 3000 ms of A, B runs 3000 ms as well. And how that's adjusted to the scheduling period is those adjusted V slices that we calculated. So every 1.5 ms that A runs, you want this guy to run 0.75 ms. So once we kind of look at, okay, is that being achieved? Then yeah, CFS is allocating the fair share of CPU to each task. So now that we've computed V slice, let's look at exactly how CFS goes about things. Let's say A is 3000 as a weight, but we'll compute the V runtime equal to 0. B V runtime is equal to 0 to start with. A V slice is 1.5 ms. B is 0.75 ms. And we also have the weights, right? 3000 and 300.
Yeah.
Yeah.
Do you think you can enable cameras so people at least get like the sound?
Yeah.
Whiteboard. Okay.
But yeah, what we have as of now is the V slice, the weight. And we know how the V slice is calculated, but how is the V runtime adjusted as we go ahead? So this is initially. Now at the initial point, we have 0 and 0. That's an arbitrary pick for the scheduler. Let's say it picks A. Now, as we discussed, V slice is the duration that a task runs for unless it's preempted, right? Now, A is scheduled and it runs for 1.5 ms. And after that, we then decide to preempt it with another task. Scheduling decision is made. But until it completes its V slice, nothing's done. So at this point, it checks what is the next minimum V runtime and then schedules that process next. Now, what we also need to do here is this 1.5 ms is the wall clock time. So we need to adjust that according to the weight of the task itself. So what that formula looks like is the wall clock time into 1024, which is the base weight, divided by the weight of the task itself. That's roughly 1 by 3. So 1.5 ms of runtime for A means 0.5 ms in B runtime. So this becomes A equal to 0.5 B runtime, B equal to 0, right? Then let's say B is chosen next because that's the minimum. Then A stays at 0.5, but B runs for 0.75 ms. Does the slice? But then that needs to be adjusted according to weight as well. So that's 0.75 into 1024 divided by 300. And that's roughly 3. So that's 2.25. So this becomes 2.25. And you can see that the difference in V runtime increasing is very different, right? And it depends entirely on the weights as well as the slices. Now, because this is the difference, A is chosen again next time. And we know that it increases by 0.5 every time it runs 1.5 ms. So this becomes 1.0 and B stays at 2.25. But you can see that the min V runtime is still A.
Yeah.
So this gets chosen again. And this continues until the min V runtime kind of balances itself out. And this is how V runtime increases in I don't know, proportion to make sure that the fair share of CPU is allocated to each task.
But it seems very unfair because we ran B only once and for a shorter period of time. So are you sure that there is no bug in this calculation?
Not in the calculation itself, but what CFS also does is it has buddy systems. It has skip buddy, next, and last. So next buddy is to make sure that you have NUMA runtime as well as I think task relationships. For example, if let's say a task is just woken up and it's not like scheduled immediately, you'll use the next buddy heuristic to make sure that it's scheduled next. Along with that, I think there is also NUMA locality, if I'm not mistaken, in the code itself. Last buddy is to make sure that there's cache affinity. So you want to make sure that the task that has just recently been run is preferred next time when you're making a scheduling decision. And skip buddy is chosen when, especially in the yield, I think in CFS, once you yield, you have made the skip buddy so that you're not really preferred next time you make a scheduling decision.
I get it. So my comment was about the fact that intuitively it felt that one would expect that A runs for 1.1, 1.5 milliseconds, and then B runs for 0.75. And then A runs again, and then B runs. But in your example, A keeps running.
The problem here is that we're just looking at two tasks when we took that 20 tasks totally, right? That's why it looks this way. But if you want to make it just like 3 tasks total and just like look at numbers that way, I think it'll make more sense. If you have the time for it.
No, don't do this.
Yeah.
Okay, but you believe that, okay, yeah, sure.
Yeah, at the end of this, what you will see at the end of the scheduling period is that for all 20 tasks, A would have run 1.5 ms, B would have run only 0.75 ms.
It's just that it felt that there was some mistake in how you calculated how your runtime is moving forward for each of them, but maybe.
Yeah, the calculations themselves
So
are
supposedly
correct, but yeah.
But wait, because we already weighted their slices, so one would imagine that their B runtime after each of them ran once should
be the same. Yeah.
Intuitively, it feels this way, right? So because it's already we weighted them, we gave them different slices, right?
Right. Yeah. I think it's because basically when I took N as 20 and total weight as 30,000. This should kind of like actually align.
Maybe you're right.
Yeah. So just the calculations themselves, the formula that we use is accurate. And the professor is right in the sense that if you take just one scheduling period of 15 ms, and let's say you have 3 tasks, not 20. If the first task runs, it'll have a VRun time of let's say 1.5. When the second task runs, regardless of what its weight is, if it completes its entire slice, it'll have the same VRun time. And so will the third one once it runs. So basically what the professor is saying is that if you have different weights, once they complete their slice, their VRun time will match regardless. Yeah. But what we need to understand from this is that this is how it kind of encodes all of the logic of throughput versus latency. And this makes it VRun time. And it completely depends on vSlice, shed period, and min granularity, which are all heuristics to begin with. Now, this is when there is no waking up or yielding, right? This is just a normal tick. So once we understand that, yeah, the VRun time changes according to the weights, and that is how it kind of balances out at the end. And at the end, it gets the fair share of CPU. Then we can kind of look at what happens when there's waking up involved. So let's just remove this stuff. let's make it 15 ms, but let's keep it at 3 tasks. Okay, actually, if we keep 3 tasks, we have to make it 6 ms. So 6 ms is the shed period, and 3 tasks is the number of tasks that we've got. And let's make that A, B, and C. And let's say C is the interactive task, while A and B are compute tasks. And let's give A 3000, B is 300, or let's say 3000, and C is 300. These are the weights of each task. And if we have to calculate the B slices, that'll be 6 into 3000, 4300. I think I've already done this before, so it's around 1.4. No, 4.2. 4.2 ms for this guy. This will be 1.4 ms, and this will be 0.4 ms. Sorry about the handwriting. But yeah, so we know that this is the V slice of each task, 4.2, 1.4, and 0.4. That adds up to 6 ms. Now, once A is chosen first, it'll run for 4.2 ms. But 4.2 ms adjusted by its weight would be 4.2 into 1000 by 3000, which is equal to 1.4. So this becomes 1.4, and B's are 0 and C's are 0. And C is still sleeping. This is the interactive task. Now, once B changes, it'll run for 1.4 ms, but it's adjusted to its weight, which is just 1.4 itself. So this becomes 1.42. Now here, let's say that C is going to wake up. But at this point, I think it's already minimum runtime, so this doesn't make too much sense. Let's run it once completely, where this in the next scheduling period becomes this should have 1.4 as well. But let's say that C runs once, it's not sleeping now, it is picked, and it becomes 1.42. Now, the reason that I had to make it run once is to show you what happens when it wakes up and how that changes the scheduling decision. Now, let's say this is at the end of the first scheduling period, right? After that, let's say that C sleeps and wakes up at this point. Now, if C was sleeping at this point and it just woke up, what happens then? So what happens at this point is it is going to be recalculated. It is, once it sleeps, it's removed from our RB tree. So when a task sleeps, it's removed from our RB tree, and the RB tree is just to make sure that we are computing the minimum V runtime on groundable tasks only. So once it sleeps, it doesn't compute the V runtime for this guy. It just like removes it from the RB tree and is taken out of all calculations. And when it wakes up again, it is placed in the RB tree first before we make any preemption calculations. When we place it into the RB tree, we take out a few things when it comes to waking up tasks. So with waking up tasks, one thing that we need to make sure of is it cannot lag way too behind, right? Because then your V runtime will be too low and you'll always get the preemption there. So you can't have the V runtime be too low. So you have to adjust V runtime to make sure that sleeping tasks cannot game the system. So if you say that C remains at 1.4, it starts sleeping here, and A and B keep getting scheduled, they get to, let's say, 100 ms each. But if this stays at 1.4 and suddenly wakes up, it cannot have a 90 ms, let's say, head start over the others, right? So you have to adjust V runtime. And how we do that is that we cap it to min V runtime. And that's calculated from the RB tree. So min V runtime is the V runtime of the leftmost node. We cap it to that and we give it a little credit. And this credit is given to make sure that it's still responsive. When a task wakes up, you want to be responsive, and this credit is chosen based on heuristics again. And that can be anywhere between 6 ms, 3 ms, all 0.75 ms. And all of these are based on heuristics and tunables. So this can get a credit out of any three of those values, but it will be given a credit. When this is given a credit, it's going to be somewhere in this region. Right? But then at that point, we're going to check if it can preempt the task or not. So preemption is different for normal scheduling ticks and for wake up. For normal scheduling ticks, if there's nothing going on in terms of waking up, it will check if the current task has run its complete V slice or not. If it's not run the V slice, it is not going to get preempted. When it comes to waking up preemption, however, we will check if it's greater than the difference in V runtime after it's placed in the V3 and the current task. If the difference in V runtime is greater than or equal to something called the wake up granularity. Now, this is another heuristic again, and this is tunable. And what we'll do here is that we adjust wake up granularity by the weight. This is the weight of the waking up task. The reason you're doing this is to make sure that the weight of the task is kind of like, giving the system some hints on the latency requirements as well. If you have a higher weight, then you mean that the chances of it preempting is higher. And if you have a lower weight, the chance of it preempting is low. That's about it. Because if you adjust it by a higher weight, this whole value becomes lesser. So the difference needs to be lesser between the current task and the waking up task. So what we're doing here is we're checking the preemption based on this particular value, wake up granularity. And if the granularity is greater than the actual difference between runtimes, the preemption does not happen in that case. And if the preemption does not happen, it waits for a scheduler tick to check if the preemption can happen there. But if the preemption happens when the task wakes up and it's lesser than the wake up granularity, or the difference, is more than granularity, then we actually preempt the current task with the waking up task. So here, let's say A is equal to 100 ms, B is equal to 100 ms. Let's say C started sleeping here, and this is when C actually woke up. Then C's new V runtime will be 100 ms, which is the min V runtime, minus the credit. And here, let's say arbitrarily, we give the 3 ms credit. It becomes 97 ms. And then let's say the wake up granularity is something like 4 ms. But I think in Linux, the default is 1. But you should know that wake up granularity is a heuristic that can be tuned. So it depends on the workload. You can change that if you need to. The wake up granularity is 1, and this is 97. So the difference between, let's say, the current task here was A was running, and at this A became 101. This was min V runtime. It chose that and gave it a credit of 3 ms and got 97 ms for C. Now, A was at 101 ms because it was currently in the midst of its cycle or its slice. So the difference between this is 4 ms, which is greater than the 1 ms wake up granularity. So this one preempts at this point. And this is how you make sure that one, you're clamping V runtime so that the task does not get an undue advantage over the rest. And then you're also checking the preemption based on the wake up granularity there. And if it messes this granularity window, the wake up window here, then it has to wait for A to complete at least 0.75 ms. Sorry. So I think it's best if I show you the code. Let's not see the code though. But yeah, as of now, we know that it's at 101 ms, right? Let's say this difference was.
Yeah, so when imagine we did preempt, so how long C will be running? Because
After preempting?
after it preempts, for example, A, so its runtime is 97, so will it run for like whatever?
No, it's less. It's V slice is what it will run for
It
unless
will
it's.
just run for its slice.
So the base logic stays the same. Without any wake up preemption or yielding, once a task is scheduled, it runs for its entire V slice. Once it runs for its entire V slice, the system then picks min V runtime and that repeats. Now, even after wake up, the wake up, all that introduces in terms of complexity is whether the task preempts and what is the new V runtime when is placed in the run queue. That's about it. Now, once it's actually scheduled, we're back to this. There's no difference in the logic there. Yeah. And when the task yields, what happens is it's set as the skip buddy, which means that next time that same task is picked to be run, it will not be preferred. You'll instead look for a task which has lesser V runtime, or for a task that has been set as the next buddy or the last buddy for cache locality. But that's how it basically maintains fairness in this execution flow. In all of this, is there any doubts about V slice, shed period, and min granularity? Or
I had a doubt about the 4 millisecond thing, like I was just wait.
the difference between the current and the waking up task?
Yes.
Yeah.
Just if you could go over it one more time, like
Yeah.
I know we're calculating the difference, but I'm not sure how the difference factors into the decision.
Gotcha, yeah. So that's again, like, based on the heuristic called wake up granularity. Let's just call that WG. So wake up granularity is by default 1 ms, but can be changed according to workloads.
Okay.
Now, what happens here is before any task is picked here, A was at 100 ms, B was at 100 ms, and C was sleeping.
Yeah.
So once A is picked, because it's an arbitrary pick between the two V runtimes, A becomes during the cycle itself. A is at 101 ms. That's when C wakes up. And B stays at 100 ms. So when C wakes up, the min V runtime is this guy.
Yeah.
And you give it a credit of 3 ms, so it gets 97 ms.
Yeah.
And what you do to check if C can preempt the current task is check the difference between the V runtime of these two. And that's a 4 ms difference. Now this has to be greater than wake up granularity, WG, weighted by the weight of C. C is, I think, 300, right? So that'll be into 1024 by 300. Sorry, I think it will be into 300 by 3000, 4300.
Or the sum of the next value.
Yeah.
The sum of the
Yeah, basically this guy will reduce, it'll be a smaller value when you have, 1 second. 024 by 300. Yes, right. Yeah, so this guy, this entire value that we'll compare 4 ms with will be smaller if you have a higher weight and be bigger if you have a lower weight. So if you have a higher weight, your chance of preempting the current task is better. If you have a lower weight, your chance of preempting the current task is worse. So higher weight means you get preference.
Okay.
So once you get this value.
Sorry, so higher weight as a, so C is the interactive process, I think.
Yeah, C is
Yes,
waking up.
Yeah, so C was the interactive process.
But we give it very small weight for whatever reason.
Yeah, okay.
Which
Yeah.
is unusual, but.
So it's not gonna get picked here.
So here will be, I think,
Because
0 to
4
2
milliseconds needs to be greater than 3 milliseconds, so it would work.
It would. So WG by default is 1 ms, right?
Yeah.
So
So,
1 into, I think, 1024 by 300 is somewhere around 3.
yeah,
You get 3 ms, and 4 ms is still greater.
yeah,
That's why it would preempt here. But in some cases where the wake up granularity is greater or the weight is lower, that might not.
so then C gets over.
But that's the decision that it takes when the task wakes up itself. But once it's scheduled, it will run for its entire slice and we resume normal process.
Sounds good, yeah.
So that's the concept of CFS and how it goes about things. Now I think we can look at a few examples of where it doesn't work. Yeah.
Well, I still don't get it. So even if C runs for the entire slice.
Yeah.
Imagine just for whatever reason, its V runtime did not catch up with the other runtimes A and B. Will it run again or not? After it ran for the entire slice.
Yeah, so let's say that it ran for its entire V slice at 97 ms and you will get a 1.4 increment like we had discussed here. Right?
No, just Yeah,
Yeah.
but just for this, I don't know those.
Yeah, you get to 98.4, and what the professor is asking is, it's still, so.
Yeah, so
Will
will
it
it
keep
will it
running
run
again?
again?
No, so basically, when we're talking about a sleeping process, we want to make sure that our understanding of this particular example is accurate in the sense that once it runs for its slice, it will sleep again. But let's say it doesn't, then it will be picked again.
So it will be scheduled multiple times until it's like year on time.
If it decides not to sleep again, then yes, it will be scheduled multiple times until it catches up to this guy, which is I think one more time. So it can run a total of 3 consecutive times until it catches up to min v runtime. And that's why we adjust v runtime here to prevent scenarios where sleeping tasks, if they decide not to sleep and be kind of like, an attack, basically, it cannot derail the throughput of the system.
But still, there is some unpredictable. It in this scheduler, it theoretically can run for a couple of slices, and even
Yes.
with all these heuristics. Right?
Yeah. So with these heuristics, you're making sure that you're preventing or damage control when it comes to attack scenarios. But at the same time, yeah, it's not perfect. And you're achieving all of this through complex heuristics. When we're talking about wake-up granularity, that's again a tunable heuristic. There's no real math behind why it has to be 1 ms or 3 ms. There's no reasoning there. It's just common sense based on your particular workload, probably. That's about it. But now that we understand this is how CFS works, we can actually talk about scenarios where it's not the best. So if I can just erase these guys. Yeah.
Say I disable all the I disable all the cores of my system except one.
Yeah.
Will it still consider all of these heuristics? Because it seems like.
It will. Yeah. So when
And
you're
then
talking
how
about
will, so your A ran for millisecond.
Mhm.
And then C came in, right?
1 ms, A, and then C came in, you're talking about it waking up.
It just seems that this scheduler will just take more time. So
Basically all of this logic that we're talking about is per CFS run queue, and you have one CFS run queue per CPU. So even if you disable the other cores, the logic stays the same. When you're talking about multiple cores,
What happens when you dynamically unplug the cores?
yes.
Well, probably it will react in some meaningful way, but
Maybe heuristics might change.
Yeah.
I guess still.
in what way would the heuristics change? I'm not.
like suddenly instead of like 10 tasks, because you were running maybe 10 tasks on each of the 4 cores.
Yeah.
Now you have 40 tasks or something, so you have to recompute something and something.
Okay. Yeah.
And probably they designed something meaningful, but
Yeah.
No, yeah, because seems like if you have multiple cores, the schedule can just keep running on one core or something. Keep doing all these heuristics.
What I do understand of the
your
heuristics,
schedulers run, each core has its own run queue and will make all these decisions private to a core. And once in a while, they will rebalance tasks, so there will be some kind of another heuristics for when to move tasks from one core to another. It will move.
yeah, even the buddy system is per core. When you're talking about last buddy, next buddy, you want to make sure that the cache locality is per core again. But tasks are periodically load balanced between cores. But when we're talking about all of this logic, it's per CFS run queue, and that's per core again. Coming to scenarios where it doesn't really work, or I wouldn't say it doesn't work, I'd just say the behavior isn't the best or most predictable. It usually comes up when you're talking about sleeper, fairness, and wake up heuristics. So let's say you have one CPU bound task that is running, and we have the same weights, 3000 for this guy, and let's say 1000 each for our interactive tasks of B and C. Now let's say B and C were sleeping, it was at 50 ms V runtime each. And A was at, let's say, 150 ms when B decides to wake up. And at that, we've done this calculation before. It takes the min V runtime and then gives it a small credit. So it gets 147 ms, right? And then this C stays at 50 ms because it's still sleeping, and A is at 150 ms. So at this particular point, we'll check if B can preempt or not. And that we've already gone over how that works. But let's say C wakes up just 0.1 ms after B. So at that point, this guy is the min V runtime, and then that's 147 minus 3 again. You go 144 ms. You can see how just waking up 0.1 ms later led to a difference of 3 ms in V runtime. So just like a small difference in the time at which the task wakes up leads to a big difference in overall behavior.
And the credit is like a fixed number. Like
It's not. So basically that depends on the jurisdiction as well, 6 ms, 3 ms, and 0.75.
But every process gets the same credit regardless of its priority or its speed.
No, so 6 ms is the default credit that a task will get. There is another scheduling feature called gentle fair sleepers that can be set for a particular task. And if that is set, then it gets 3 ms. And if it's an idle task, it gets 0.75.
Got it.
But yeah, depending on those, you get a credit, yes. But then the task waking up just 0.1 ms different also will lead to a big difference in VRAM. And that's just something that you can't avoid because you've set up all of these heuristics to make sure that the fairness is maintained over time. So short time latency can suffer because of this. And also when you look at min granularity, right? When we initially start off, everybody's at 0. And we know that min granularity is set at 0.75. But let's say when you actually adjusted the V slice according to the weights, C was supposed to get something like 0.1 ms. And B was supposed to get something like 0.3 ms. But initially you can't give it something that small because of that. So you get, let's just say A ran for whatever amount of time. But B and C also ran for 0.7. Oh, let's not look at V runtime because it won't really give us exactly how much overclock time it got. Let's say this ran for 1.5 ms on the CPU. This will run for 0.575 ms, and this will run for 0.75 ms as well. But actually, this is what we need to give it for scheduling period at all. So because this gets a big chunk of its runtime well in advance, it's not run for a long time until this catches up with the V runtime proportion according to this one. So let's say that C was supposed to get 0.1 ms, B was supposed to get 0.3, and A was supposed to get some ungodly number like 2.5 ms. So the difference between these guys is quite a lot, right?
But these are the V slices, right?
Yeah.
But then, like, since 0.1 is less than 0.75, why are we even considering 0.1?
No. What I'm saying is that this is what the proportion is supposed to be. But because of
Oh,
this
right.
min granularity, we can't give it this.
Yeah, so the proportions
Change.
you will follow is
Yeah.
2.5 to
So the algorithm does not consider 0.1 and 0.3.
Yeah, okay.
Is that we know that according to the weights that we've given these guys, they're supposed to get much lesser than the algorithm actually gives it. So short-term granularity will, short-term fairness will suffer, but they will eventually catch up to this
Okay,
proportion.
actually this will.
Yeah. But short-term,
Oh, because the
Fairness.
delta runtime, the runtime added is based on the priority.
yeah, so that grows like, in proportion with that, not the V slice. But yeah, at the short-term fairness will suffer when it's initially shaded. So this is another example. And when we're talking about wake-up heuristics as well, we saw how just like a small difference in when it wakes up leads to a big difference in V runtime. But also, if you just look at the logic itself, the placement in the run queue depends on this, which is again not really fixed. You cannot really predict it. Along with that, it depends on the min V runtime that was prevalent when the task woke up. So that's a heuristic as well. That's not predictable. Along with that, the wake up granularity, which decides whether you preempt or not. This is the heuristics in itself. Like you don't know why it's given the value that it's given. And it's not really conducive to a predictable behavior over time. So these are some examples where it doesn't really work the best. I wouldn't say it's got any issues where there's gaming possibilities because it was the prevalent scheduler for about 17 years. So it's not that it can be gamed, but it had a bunch of heuristics, which is not really math based, not mathematical. and it kept getting more complex over time. And I think just like the straw that broke the camel's back was when they were deciding to whether include nice latency patches or not. So to discuss this guy, right, to really understand what this is, we discussed an example of CFS where you can give it weights and you can give it a share of CPU time over like, a bunch of MS like the scheduling period, but you cannot give it an urgency or a latency metric for the task. So what I mean by that, let's keep this here. What I mean by that is if I have one task that is CPU bound and is not very latency sensitive, it can tolerate latency up to like 100 ms. But let's say another task is very latency sensitive and needs to run every 5 ms. There is no real way that you can specify to CFS that I need this guy to run every 5 ms. There's no urgency or latency metric that I can give it. I can only give it a high weight. And how this helps is that it is scheduled more often because its V runtime grows slower. V runtime. And it is scheduled, I think the wake up preemption also is preferred when it has a higher weight. So that is another advantage as well. But apart from these, I can't exactly specify the urgency or latency of task B, which is why I think they were talking about nice latency values, where you would give it again a nice latency value of plus 20 to minus 19. And based on this, your wake up granularity value and the wake up preemption would change. And because of the added complexities and just like the unnecessarily interactive heuristics, they decided that okay, fine, let's just shift to EVDF. And the reason this happened is also not that okay, fine, this is just like unfathomable. We've got to like reinvent the wheel. EVDF was already published in the 1995 paper, and in 2003, there was an implementation of EVDF already out there. And I think at this design decision, they decided to give this a go. And this was added, sorry, not 2003, 2023. And this was added, I think, in 2024, just last year, if I'm not wrong. But any questions about nice latency values? I think it's not very important in the big picture. Just that, yeah, there was no way to actually specify the urgency or latency of a task. Now we can actually go into like EVDF and see how that works in comparison to CFS and how it actually replaces one, the heuristics, and two, gives us a way to look at latency sensitive workloads in a more mathematical and predictable way. Let's read all of this.
And maybe it makes sense to ask the class at this point whether people see this possible solution to those problems.
Yeah, as in like
some people can
yeah.
suggest it.
Is there a way that you think you can kind of take CFS?
Or just maybe even like completely different scheduler.
Or maybe scheduler, and make sure that we have this throughput versus latency trade-off. TP versus latency. Make sure that we have weights and prioritized scheduling where throughput bound tasks get a fair share of CPU according to their weights, but make sure that we have latency priorities as well. We can mention the priority of latency of a task A or B and say that A or B has an urgency to run every 5 ms, or if there's like a scheduling decision to be made, prioritize B over A.
If the latency sensitive task is like sleeps frequently, I would try to game it with the credit system. So based on like its sensitivity, the credit that it's given when when it wakes up will maybe be increased.
So the placement in the RB3 would change.
Yeah. Sorry.
So once you change the placement of the task in the RB3, let's say that you find a way to always make it the leftmost, right? But then what about the actual preemption logic? So the preemption logic takes the difference between the waking up task v runtime, the current v runtime,
Yeah.
and then computes that with relation to something called the wake up granularity.
Right, that's right. Yeah, I would kind of override that, I guess. I wouldn't put that. Like, this is a fairness metric, right? The wake up grandpa.
Yeah.
Yeah, so we want to create an environment for some unfairness for these latency sensitive tasks.
Yeah, yeah. You can't look at strict fairness when you're looking at both responsiveness and throughput.
So if I'm asking for extra credit, I will skip the fairness check with this wake up grandpa.
So you would give this extra credit based on what?
The sensitivity, if like however we could define that sensitivity. That it needs to wake up every X milliseconds.
Okay.
If we can encode that in like the metadata of the task. somehow.
Okay. So let's say it's a shared attribute that's passed from the task itself.
Yeah.
Is it like adding one more heuristic?
More like if we can give it a like a priority, then we can give it an urgency as well.
So you're taking some input from the task to define this latency,
yes.
and based on that, you're changing the credit that you're getting.
Yeah, so if a task is getting a non-standard credit, then we will skip the fairness check. It's like if it's above a certain tax bracket, it won't get taxed, like how the reality.
Yeah, but the problem is that you would have to kind of mess with the core workflow.
Yeah,
of-
yeah.
Yeah, and
You
give it
have to
another
skip like an
exception and
entire
another
process.
heuristic.
We add like a higher level scheduler on top of CFS.
It's like, okay, make this like the sub
Yeah,
scheduler and have another scheduler on top, and what will this get?
yeah.
CFS is for all tasks with the same.
No, and then like, yeah, and when such case arises, so all the tasks
Yeah.
will need to go through that higher level scheduler
Okay.
for CFS to schedule it.
Mhm.
And when you have some tasks like A or B, you can like kind of reduce the other tasks which go into CFS, have a queue, waiting queue,
Mhm.
and only push in A and B. So naturally, you have like less number of processes in the CFS, so A and B will like, again, it's not a mathematical guarantee, but still like,
Yeah, yeah.
you still have a queue of waiting tasks and not, CFS is not handling all the tasks. It's going through the books.
Yeah, so one thing that we saw is that it's just adding on to the heuristics. Second thing that we saw is that we'll have to reinvent the wheel. We'll
Yeah,
have to
in this
break
case-
the core workflow that we have for like all tasks and have this be a completely different exception.
No, so I'm not changing my CFS, I'll just add a layer on top of it, so my CFS won't change at all.
Yeah.
But it's just that all the tasks will be scheduled through X.
Look, hold on, maybe let's move on to the earliest deadline first, otherwise
Yeah.
I'm not finished today.
But yeah, so we can think about a lot of different ways to do this, and this is not a little too far off from what actually people are considering before moving to EVDF.
Yeah, when people talk about.
What they were actually thinking about, yeah, it's not actually too different from what was discussed before. But what people are actually considering is giving it a nice latency value each task. So it's not too different from what you were suggesting. Only thing is they wouldn't change the credit. The credit system would stay the same. Only thing is this would change the wake up preemption logic. The wake up granularity value would change based on the nice latency.
Okay.
But
So yeah, pretty much the same thing. You're just
Yeah.
applying it a little bit.
only thing is, this was considered just going in the wrong direction and for far too long. Because it was just adding on heuristics every time they saw some bottleneck or some tunable. So they decided, okay, fine. We had this paper in 1995 and somebody's implemented this in 2023. Let's see if we can make that work. So that's when EVDF comes in the picture. And what we do here is we simplify a few things and we add on a few metrics. So what we did with CFS is we only looked at VRuntime. And because we only looked at one metric, we had to introduce a bunch of heuristics to make things work. So instead of that, we make sure that with EVDF, we have something called lag and deadline. So these guys are additional. And what this means is that we remove a few things when it comes to heuristics as well. There is no wake up granularity. There is no shed period. There is no min granularity. So these are the main heuristics that we had seen with in terms of the normal workflow for without waking up or yielding normal scheduling behavior dependent on these two guys, right? Very core to the logic itself. And for waking up tasks, it depended on makeup granularity as well. So we remove all of these heuristics, and you can see that when we discuss EVDF in the function well for the next 20 minutes or so, you will see that we don't talk about a bunch of heuristics. The heuristics are replaced by these guys. And what is lag and what is deadline? So we understand how VRun time works in CFS. It's not too different in EEVDF. What we do here is we take a base slice. Now the base slice is the same for all tasks. It's 3 ms by default. Now what we do with the base slice is we weight that according to the nice value of the weight of the task itself. So that's, let's say we have A, B, and C. We took the same numbers that we took last time, 3000, 1000, and 300. So the base slice is adjusted according to this by saying that it's 3000, 1024 divided by 3000. Now you can see here that in CFS, if the weight was higher, you would get a bigger slice, right? And why we wanted that to happen is that over time, the higher weight tasks get more CPU time than the lower weight tasks. Here you will see that the slice reduces, becomes smaller, or is inversely proportional to it. You'll have a smaller slice if you have a bigger weight, and that means that this becomes 1 ms for A. For B, it's 3 into 1000 by 1000, so it's 3 ms. And for C, it's 3 into 1000 by 300, which becomes about 9 ms. And you will see that A has the most weight, but has the smallest slice, and so on, right? So that is one difference in how VRun time. This is the slice. This is how the slice is computed here. We take a base slice of 3 ms. There's no min granularity, there's no shed period, none of that. It doesn't change with the number of running tasks as well. Once you have the slice, the VRun time logic is still the same. It's the wall clock time into 1024.
One would assume that it does depend on the number of tasks because you divide it by 3000, which is a total weight or something.
Oh no, this is the weight of the tasks.
The weight of the task.
Yeah. So this is 3000,
Yeah.
1K, and 300. So this does not have anything to do with the number of tasks or the total weight itself. VRun time still stays the same. It grows slower for higher weighted tasks and faster for lower weighted tasks. The formula is also the same, which is 1024 by weight. Now, when we come to lag and deadline, that is where we have newer concepts and we'll understand exactly how it replaces the heuristics that we had before. So how we went about in CFS is that you had a task, it ran for its slice, and you pick the min VRun time. Now here instead what we have is you have a task, it runs for its slice still, but then you pick EEVDF and then you repeat. And what is EEVDF has to do with both the lag and the deadline. Lag is to make sure that you pick only tasks eligible to run. And how do you decide when a task is eligible to run? When it is behind average VRun time. So when you have this RB tree here, previously what we used to do is we used to keep the RB tree ordered by VRun time and pick the leftmost node, which had the min VRun time. This time, however, we're gonna order this by deadline, and we're gonna have something called lag to understand if it's eligible to run or not. So what we're gonna do with this is first we're gonna define lag and deadline. Lag is equal to average VRun time minus VRun time of the task. That's what it is. And deadline is equal to VRun time of the task plus its vslice. So we'll understand why these are the definitions for these terms. Lag we know is what we're going to use to understand if the task is eligible to run. If it's behind the other tasks, then it's eligible to run. If it's already run its fair share, then it's considered ineligible. So how we decide that value is average VRun time of all of the tasks in this tree. So if all of the tasks in this tree have run like different run times, and the average runtime is 350 ms. Any task that has a V runtime of 300 ms is considered eligible to run because it's behind the V runtime, average V runtime of the tree. Anything that has anything above 350 ms, if you have a task of let's say 400 ms, then it's got a lag value of -50 and it's considered ineligible. This one's got a lag value of +50 and it's considered eligible. So this is the average VRun time. Let's take the value of 350 for this, just as an example. If the VRun time here was 300, then it would have a positive lag, meaning that it's behind. So all of these tasks.
Well, aren't you just adding too much heuristics? Like, how is it?
Yeah, let's see how it converges.
Yeah, because one thing is when we talk about heuristics, we're talking about arbitrarily picked values that don't really have a mathematical backing. But V runtime wasn't a heuristic in CFS. It was something that we picked based on the nice values. And it would mathematically increase over time. That was something that we knew exactly how it would increase based on the slices. But when you talk about wake-up granularity, when you talk about min granularity, these are values that we picked without any mathematical backing to them. And that's why it's called a heuristic. But here, when we're talking about V runtime, is not a heuristic at all. And when we can talk about lag, we know that the average V runtime will increase for the entire group, right? Now, in this particular context, when you have a task that has not run, now the average is let's say 10 ms here, 20 ms here, and 40 ms here. When you have a task that is run at this point, when the average V runtime is 20 ms, you have tasks that have run 5 ms, 10 ms, and 15 ms. Those are considered eligible, but anything above that is considered ineligible. Now we'll look at this in an example and that'll make a lot more sense about how it converges. But just know that lag is going to be the eligibility metric. Once you have a positive value for lag, then you can actually schedule it. It's an option to be picked. But the actual picking as to which task is selected depends on the deadline. Now, this is where the V slice comes into play because this is the V runtime plus V slice. Now, how we saw before, if you have a higher weight, you have a lower V slice. So that's where the weight of the task comes into play. Because your V runtime will grow slower based on your weight. So this value will be lesser if your weight is higher. And your V slice is smaller if you have a bigger weight. So both of these are smaller if you have a bigger weight. And it's higher if you have a smaller weight. So once you have a bunch of eligible tasks, let's say you have 5 tasks that are eligible based on the lag value, you will pick the task that has a minimum deadline based on both the V runtime and the V slice. So that is the additional terms that we have. Now let's look at an example to really understand how it works.
But what is the intuition behind it? So how do we express the fact that the task has to run every 5 milliseconds?
Yeah, so lag actually comes up to combining all of these. So the lag itself is there to make sure that a task is not scheduled too frequently when it has very small V slices. So if you look at CFS, if you had a very small V slice but a very big weight, it would run continuously until the V runtime caught up. Right? So if you had a slice of let's say 3 ms or let's say 0.5 ms, as in your V runtime would increase by 0.5 ms every time you run your slice, it would take a long time for you to catch up with the rest. But here what we're doing is we want to make sure that the V slice is small when it has a high weight. And you should also keep in mind that this is not the only way to determine the V slice. You have an additional way of mentioning a custom slice. So this comes directly when the professor asks how you can actually mention that this task has to run every 3 ms. If you have a particular constraint like that, you will mention the custom slice through shared attributes. But if not, these are the default metrics in place to make sure that higher weighted tasks get scheduled more frequently, but in a mathematically sound way. So the V-slice will be smaller when the weight is higher. But if you want a task to have a particular slice duration, you can custom mention it as well. Now, once you have the slice mentioned, the lag is to make sure that the task is not scheduled too frequently. So in CFS, if you add a small slice, it would make sure that the V runtime caught up by scheduling it more frequently. But in lag, you want to make sure that, yeah, you have a smaller V slice, yes, but you're not going to make sure, you're going to make sure that this does not monopolize the CPU. And that's why the lag metric is present, where if you are scheduled consecutively, you will grow faster than the average V runtime because the other V runtimes are not growing. So once you grow faster than the average V runtime, you are not going to be scheduled anymore. So that's the intuition behind lag, is to make sure that, yeah, you will be prioritizing slices with smaller slice durations, but they will not be monopolizing the CPU. So that's the intuition behind it. And for the deadline itself, the intuition is to prioritize tasks with smaller requests. So the V-slice is seen as a request for CPU time, right? Every time I'm scheduled, this is the amount of time I want to run. So if you have a smaller request, you are prioritized because you are adjudged to be a more latency sensitive task according to EVTF. So that's the intuition, yeah.
Deadline makes a lot of sense to me.
Yeah.
Lag, I see how it works. I don't see the point of it because I feel like based on the deadline metric, like if you sort all your current processes by lag or by deadline, you will have the same.
You're already doing that with the RB tree. So this is deadline sorted. But if I always pick the minimum deadline here, right? What can end up happening is that if I have a latency sensitive task.
One question in the deadline, you computing the V runtime or average V runtime?
No, is the V runtime of the task itself plus the V slice of the task. In the lag, you're taking the average V runtime of the entire tree and you're subtracting it from the V runtime of the task. So yeah, coming to your question, right? Why do we even have the lag? So if you keep picking the minimum deadline, let's say we have a latency sensitive task that has a very small V slice. Right? Once this is scheduled, let's say it completes this V slice, but its V runtime will also grow slow. And its V slice is small anyway compared to the other tasks. So this will keep getting scheduled more and more frequently.
Because it goes further down.
Yeah. And if you actually had to introduce fairness here without lag, you need heuristics again.
But wait, I agree with Soham actually. So, but I'm it seems that lag only averages your V runtime, right? So that's still.
So this process, you said the V runtime will grow the slowest.
For a higher weighted task.
Yeah, like the
In this context that we took, we have a high weight task, which has a very small slice.
Yeah.
And if you just took the deadline itself, you would schedule it too frequently.
So, but lag is just an eligibility metric, right?
Yeah.
So if this has the lowest increasing V runtime, it will always be eligible because it's going to have a positive value for lag.
No, it will eventually become negative because V runtime will grow slower compared to the other tasks, yes, but it will grow faster compared to the average V runtime. So you have V runtimes of, let's say, let's look at an example. Maybe that will make more sense.
Sure, yeah.
Because then you can actually see how the V runtime grows and how the global V runtime or the average V runtime grows and how it kind of all makes sense. You have A, B, and C. Let's take 3000, 1000, and 300. You have the base slice of 3 ms. And I think we already did this calculation of 1 ms, 3 ms, and 9 ms. These are the slices itself. Now, because it's got 3 metrics, we don't just need V runtime, we need deadline and lag as well. So V runtime is the first value that I'll put here. Everything 0. Lag is also 0 because it's just average V runtime minus your V runtime. And then you have your deadline. Deadline is 0, which is the V runtime.
Plus V slice though. Right?
Plus, yeah. V slice of 1.
Yeah, okay.
Here is 0 plus 3, 0 plus 9.
1.
So this becomes 1, 3, and 9. Now, how does EVDF actually work? First, it finds the eligible tasks,
Which are all of them now?
which is positive lag, which includes 0. And this is all of them right now.
Yeah.
After that, it looks for the minimum deadline, right? Earliest eligible virtual deadline first. So the earliest deadline is the smallest deadline.
Yeah.
So deadline should be the smallest. So it takes A. Now A is chosen here, and A runs for 1 ms. So that becomes 1, the V runtime.
Yeah.
Now the V runtime is adjusted by the weight itself. So that V runtime calculation does not change. Is equal to wall clock time into 1024 divided by weight. So what this means is that the time will grow slower if you have a higher weight. So 1 ms actually becomes 1 by 3, right?
Yeah.
So that's 0.33. And then the lag is 0. Oh, sorry, it's not 0. The lag becomes 0.3 by 3.
0.1.
Yeah, let's just make it 0.3 ms for simplicity. 0.1 is the average.
Yes.
This
So it'll
thing?
be minus
Minus 0.2. So it's got a negative V runtime at this point. I mean,
Yeah.
negative lag at this point, right? And then this becomes
1.
0.3, which
Plus
is the V runtime, plus 1, which is 1.3. And B stays the same. 0 is the V runtime, C is 0 as well. But the average V runtime changes, so the lag changes. So this is 0.1, so it's a plus 0.1 and a plus 0.1. And these guys don't change because the V slice on the V runtime, which did not change at all. So these both have positive lags, and this one is a negative lag. But this is not eligible anymore. We go back here, it's just B and C. And then between these, you take the smallest deadline.
Okay.
So what lag is doing here is to make sure that, okay, you know what, A has already got its fair share for this point right now.
Yeah.
So we won't be running this anymore. So that's what lag does. But what deadline does is it picks the one with the higher latency requirement, which is by the deadline. If you have a smaller slice, you have a higher latency requirement. So you pick this guy. And what happens next is you have B. A doesn't change much in terms of V runtime, but the global V runtime will change, right?
Yeah.
So first we need to see how long B runs. So that's 3 ms. But that's 3 ms adjusted by the weight, which is still 3 ms. So that's
All right.
3. And then C doesn't change because it's not run. So what is the global
1.1.
average V runtime? Is 0.1 plus it ran for 3 ms here. 3.
Oh.
Yeah.
Oh, we won't average the 0.3 and the 3.
So this is already averaged.
Right.
So you're incrementing it, right? So this one lag or global runtime plus equal to average of the last scheduled runtime. So basically it becomes 0.1 plus 3 divided
Where
by
did you get 0.1? I thought that I was thinking we're gonna average 3.3 and 0.
it kind of becomes the same thing. Yeah. Because the average doesn't change much that way. So if you take this one, it's
Or you just divide it by 3. That's what
3.3 by 3 becomes 1.1. So this is the average V runtime. So here it's 1.1 minus 0.3, which is about still minus 0. What is it?
8. No.
Yeah, good point. Yeah. And then that is correct, right?
Yeah.
No, it isn't. So it's
No, it
average
is.
V runtime minus V runtime. This guy becomes positive again.
Yeah.
So 0.8 also 0.8. And then 3 and 1.1. This becomes minus 1.9.
Yes.
And this stays at plus 1.1.
Yeah.
So right now A and C are eligible. And what about the deadlines themselves? 0.3 plus 1. So 1.3 still. This guy is 3 plus 3, 6. And this guy is 0 plus 9, 9. So this is 1.3, this is 9. So you can see here that A and C are now eligible, but B is not because it's just run. So lag again, make sure that you're spacing these guys out. You're giving them the fair share of runtime, yes, but not consecutively. Now at this point, you of course pick this guy, right? Between A and C, you have a smaller deadline of A. And why is that? You have a higher weight. So it does what CFS did by actually picking the tasks that have a higher weight, but you're also spacing it out using the lag. And when you mention the custom slice, you can actually reduce the slice as small as you want it to be. And it will get this amount of runtime every time it's scheduled. And the smaller it is, the quicker it is scheduled, like period. And this goes on going forward. But you can see now that by taking deadline and lag, you don't need min granularity.
Yeah, but it's not clear why this works. Like, what is this mathematical foundation which explains why gives you any meaningful property?
So what we're looking at with EVDF is not actually reinventing the wheel in terms of like fairness. So what CFS did, EVDF kind of builds on without the heuristics. So you remove the heuristics from CFS and you remove the unpredictable nature of it when it comes to waking up, sleeper fairness, body heuristics. You remove all of that unpredictability and you actually accomplish this with just the math itself, which is lag, deadline, and B runtime. And these are called mathematical as opposed to heuristics because this is increasing predictably based on the same formulas.
You assert that it's, I mean, I don't even see why it's fair. Like, it's not trivial to see that we achieved anything with these formulas. There probably were some proofs in the papers, which. I mean,
Oh yeah, the mathematical proofs were a little like, intense. But what you can kind of see over time is that the proportional runtime of A, B, and C based on their weights will be approximated, just like CFS as well. So you will still have the fair share of CPU for A, B, and C. At the same time, you will make sure that A, B, and C are being run. Frequency of A, B, and C are to do with the weights as well. And if you want to really fine grain the frequency of how often A is scheduled, you'll use custom slice. And the reason
so do we have some kind of a theorem which says that the first fact that you mentioned is A, B, and C will be, the CPU will be shared proportionally to their weights, but the frequency should probably be what, proportional to the slice size, or how does it work?
Yeah, the frequency is proportional to the slice size, but the slice size, if you don't mention a custom slice, it is coming from the weight itself, right? So the frequency or the default metrics that EVDF works with is that if you have a higher weight, you will be given the proportional time, but also the latency of those particular tasks will be prioritized. So if you have a higher weight, your latency will be lower because you are going to be prioritized compared to the other tasks with lower weight. So let's say at any point of time, you have 5 tasks eligible. You will pick the one with the greatest weight, basically, because that will have the lowest deadline. So that's the intuition behind it. But once you actually see it in play, you will see that lag does a very good job of making sure that these tasks are not monopolizing the CPU. as well as deadline makes a very good job of making sure that the ones with higher latency requirements are prioritized compared to the ones with lower latency requirements.
When you say get rid of all your heuristics, things like the cache affinity and all that.
No, cache affinity is still a part of the heuristics that you've got, but you will see that it's much simpler. If you actually compare these functions in both of these schedulers, right? For example, if you look at, is it doing what I think?
So like again, a simple example, imagine one task was sleeping for a while. When it wakes up, so supposedly it will be, the lag will be huge, right?
Yeah, so we have to come into like the
It
wake
will
up
manipulate the
Yeah.
CPU intuitively unless you implement some heuristic for like adjusting.
How to adjust the lag, right? So what happens when you have a waking up task? So this is how, when you're trying to understand how a scheduler works, it's best to kind of see what happens if there is no wake ups or yields, how exactly it works just based on like, the weights of the task themselves. That is how you see, okay, fine, is the proportional runtime being given? How often are they being executed? What is the latency trade-offs? But once you have the waking up behavior included, so what happens when a task wakes up? First things first, it's added into the RB tree. And how you add into the RB tree is, this one's based on the deadline, right? It's not based on the V runtime anymore. But at the same time, you have these other things about V runtime and lag as well. So when you add it to the RB tree, what really matters is average V runtime, because this is central to our lag calculations. And when you add it into the RB tree itself, if the average V runtime changes, the lag values of all of these tasks changes. So you want to make sure that the average V runtime does not change. So what you want to do is when you add a task into the RB tree, you will scale lag. So when the let's say A was the task that we're talking about, it slept when it had 50 ms V runtime, and its lag at that point was plus 20. So when we add it back into the tree, we wanted to stay at plus 20, because when it's sleeping, we make sure that the lag is not changing. We're preserving the lag, and the V runtime and deadline can be adjusted. What really matters to us is the lag itself. So when we preserve the lag, we want to make sure that the lag is scaled such that the average V runtime does not change. So let's say here it was plus 20, right? So we will change this lag value such that when you're adding into the tree, the average V runtime doesn't change. And why that's the case is V runtime is equated into average V runtime minus lag. So we took this plus 20, we scaled it into X. We use this X to calculate the V runtime of the new task when it's added into the tree, and as the average V runtime of this tree minus lag. And why we're doing this reverse engineering is that if you think back to what lag was, it's average V runtime minus V runtime. So what we're trying to do with all of this is to make sure that this is preserved and average V runtime does not change. So we change the lag value, we calculate the new V runtime. So the V runtime will change when it's added back. The lag value will be preserved. Average V runtime will stay the same, and the deadline is recalculated based on V runtime plus V slice. But what we need to know about all of this is that the lag stays the same, average V runtime stays the same, and when the task wakes up.
Yeah, then you're also out of time.
Again?
1 minute over.
Okay. But yeah, I think
your final comment.
Yeah, this is the last bit.
Hope we'll never see this again.
EVDF. So when you wake up, you have the same lag, and once it's placed in the RB tree, you're basing your preemption on what the deadline is. It's no longer based on the wake up granularity.
Right.
If the deadline is before the deadline of the current task, you're good, you're preempting. If it's not, you're not preempting. That's about it.
Is there a paper which compares?
There's no paper that actually compares these two. There is a paper that compares the behavior or performance of these two, but not exactly the logic of itself. So what I can do is send you guys a document about the actual code, the source code, how it works. And I can give you some resources that talk about the performance changes. as well as the improvement in terms of how mathematically founded it is. That we do have to source. Yeah. Thanks, guys.
So the way I see it is that this lag is sort of like a binary classifier. Adjusting the rerun, yeah. So rerun time is like the distance from the threshold of the class.
Yeah.
So that's why increasing rerun to maintain that distance